Hi everyone, good afternoon. My name is Saad Said and I am a second year PhD student from Electrical Engineering Department of Information Technology, University, Pakistan. Myself and my colleagues Dr. Abdullah Nafis and my PhD supervisor Dr. Usmani Yunus, we have put this work together and I feel so grateful to present our work in this prestigious event, OPTICA Imaging Congress. So, the title of our work is FSO beam propagation analysis for fog attenuation and atmospheric fluctuations under controlled environment. Before starting, I would like to acknowledge the ITU and Higher Education Commission of Pakistan for funding this work through NRPO grant. Furthermore, I'm also grateful to the OPTICA Society for accepting this work and allowing me to give a talk in this esteemed event. So this is a quick overview of this presentation that will be followed by a brief introduction of free space optical communication. Then we will look at the channel effects on beam propagation. After that, I will describe some reported experimental setups along with the designed atmospheric chambers. Then I will present our proposed fog attenuation model in comparison with Kim's model. Based on the measured data, we have calculated the atmospheric turbulence, that is basically the Cn square. And finally, we have calculated the atmospheric coherence width, that is basically the Fright parameter. Now, this is a brief introduction of FSO, which is a physical layer technology that transmits data using optical wavelengths over free space atmospheric channel. A basic FSO link design is given here, where the data is sent from the source and converted to the optical signal, which further derives the laser diode or the LED source. The transmitter optics here perform the beam shaping, and this optical beam is propagated in free space channel, that is the air. There will be some atmospheric effects on this optical beam, which I will be discussing in upcoming slides. So normally the FS operating wavelengths fall within the range of infrared and visible spectrum so that we can achieve the high speed communication up to the terahertz. Here a few FSO transmitter designs by LightPointe, Google X, and Coruza have been mentioned. The motivation behind this work is the global demand of the internet, which is rapidly increasing by every year. Current physical layer technologies like radio frequency spectrum are not enough to cater this global demand. Then, how do we achieve the high capacity networks? If we consider the unguided medium, it can be achieved by deploying wireless microwave links. But again, this is a physical layer technology which has the limited spectrum availability and high license fee. So there is a need to explore efficient alternatives. FSO has emerged as a viable alternative as it offers numerous advantages such as high bandwidth, unlicensed band spectrum, low cost transceivers, and quick installation. So we can say that as a global demand for internet connectivity continues to surge, the adoption of FSO communication offers a promising path forward. Now we are going to discuss the atmospheric channel effects on the beam. The atmospheric channel is by nature a complex and an unpredictable medium that causes the atmospheric turbulence. The propagating optical beam that undergoes the effects like scattering and absorption in the random atmospheric conditions such as fog, rain, dust, smoke, etc. The refractive index of air is affected even in the clear weather due to the thermal gradients from the sunlight heating. So the refractive index structure parameter is used to measure the atmospheric turbulence strength that has been given in this table, as the Cn square values are changing from 10 raised to the minus 16 to 10 raised to the minus 3. This indicates that the turbulence is going from weak to the strong. So these are some experimental studies reported by the authors to analyze the beam propagation in a specific weather conditions such as fog, smoke, rain, or dust. It is very difficult to it is very difficult to repeat the measurements under identical weather conditions because the occurrence of these conditions cannot be predicted. So controlled atmospheric chambers are required to create such weather conditions. These authors have conducted some groundbreaking but initial investigation by using the controlled atmospheric chambers, and these authors have also proposed the empirical models that are very close to the actual environmental conditions. Following up the previous work, this is our designed atmospheric chamber that is made up of transparent acrylic sheets that have a total dimension of 100 by 38 by 38 centimeter cube. These are the hardware specification of our chamber. Here we have employed two CNI laser modules at transmitter site. First one is the 532 nanometer operated at 2 milliwatt for the calculation of visibility, and second one is 633 nanometer operated at 4 milliwatt for the actual transmission. Both wavelengths are from the visible spectrum to analyze the dependence on fog in a controlled atmospheric chamber. We have also employed a power meter at the receiver side for measuring the received optical power. We have employed temperature sensor and pressure sensor. We have also employed a humidifier machine to create the effect of fog, and we have employed a heater blower to create the effect of temperature gradients. All of these sensors are connected to a microcontroller for the real-time data acquisition. The link visibility is used to characterize the intensity of fog. So we are going to characterize the fog in terms of visibility. So according to Cauchy-Miller law, visibility is a distance at which visual contrast of an object drops to 2% of its original contrast. Here in equation 1, we can see that the visibility is a function of this threshold value. Again, this threshold value is from the Cauchy-Miller law is 2%, that is 0.02. So in equation 2, the attenuation is given in terms of this transmittance. That is basically the ratio of received optical power in fog to the actual transmitted power without fog. And this L is the length of the link in our case, which is 1 meter. So based on these calculations, we have characterized fog into the light, moderate, thick, dense categories for these visibility ranges. Like for 500 meter to 1000 meters, it will be a light fog. For 200 meters to 500 meters, it will be a moderate fog. And for 50 to 200 meters, it will be a thick fog. And where the visibility is less than 50 kilometers, that will be dense fog. So this whole experiment was performed for 10 repetitions. First of all, the chamber was initially filled with fog until the transmitted optical power drops to its minimum value at receiver side. Then the received optical power was observed for 30 seconds and made at an interval of 0.1 second. Finally, the fog particles gradually escape through the small air vents and the optical power returns to its initial value, that was the 4 milliwatt. Here in this plot, we can see that the received signal power against the time. This graph shows that the measured values here depicts very low divergence for all repetitions, which demonstrate the capability of our experimental setup to produce same results under controlled environments. And these are some various channel conditions such as clear channel, dense fog, moderate fog, and beam scattering in the fog. Secondly, this is our fog attenuation model where we calculated the optical attenuation versus visibility. It can be seen that the attenuation and the visibility have a reciprocal relation. For dense fog, where the visibility is extremely low, like it will be like less than 50 meters, at this point, the attenuation value is about 400 dB per kilometer. Gradually, from dense fog to light fog, where visibility is around 1000 meters, here the attenuation is only 23 dB kilometers. 23 dB per kilometers. So based on the Mayer data, this is our proposed optical attenuation model. Attenuation is equal to B into V raised to power minus A. Here, this attenuation model is in terms of visibility, and this A and B are the power law coefficients with these values. So our proposed model is in very good agreement with the Mayer data that is shown in the red dots, and our proposed model is shown in the blue line that are actually coinciding with each other. However, the proposed model attenuates 1.5 times more to the Kim's model that is given in pink line. So this 1.5 times more attenuation shows that the optical signal attenuates more in the atmospheric chamber as compared to the outdoor conditions. Now, for the calculation of atmospheric turbulence, we introduced a temperature gradient within the chamber by keeping one end of the chamber at room temperature and by blowing hot air from the other end of the chamber through a heater. The strength of the atmospheric turbulence is called refractive index structure parameters, that is Cn square. From equation 4, we can see that the Cn squared is a function of pressure and temperature. Here, in our case, the pressure is kept constant because of the fixed altitude. So the Cn square value is only getting affected by temperature. This Ct is the structure parameter of temperature that is getting affected by delta T and R. This delta T is nothing but the temperature difference of sensor 1 and sensor 2, and this R is the distance of sensor 1 and sensor 2. So Cn square value is getting affected by temperatures. So according to this formula, we can calculate the Cn square for the temperature range of 25 to 42 degrees centigrade, which has been shown in this table for 5 different instances. According to this table, we can see that the Cn square value is getting increased by, for the increasing temperatures. So this plot here shows that the Cn square and the values of Cn squared and temperature gradients are in a direct relation. from which we conclude that atmospheric turbulence strength increases for rising temperature gradients. Moreover, I would like to highlight that our calculated CN square values are in a good agreement with the reported CN square values of previous published works. Finally, the atmospheric coherence width is called Fright parameter, which is a function of Cn square and distance L. Here, we can see that the Fright parameter is a function of Cn square, this K square, and this L. This Cn square is the structure parameter, and this L is the length. This K square is the K is the here wave number of the optical signal. So from this plot, we can see that the atmospheric coherence width is decreasing for rising temperature gradients. So we conclude that the coherence width of 633 nanometer is higher than the 532 nanometer. That indicates the higher wavelengths can perform better for given temperature gradients. So that's it for my presentation. This is a conclusion and some future direction. What we have done is beam propagation of 633 nanometer is analyzed through designed atmospheric chamber. The fog attenuation model is proposed and compared with the Kim's model that is 1.5 times more attenuation gives in our proposed model. And this Cn square have been calculated for different temperature gradients. And from this Cn square, we have calculated the strength of atmospheric turbulence, and we have also calculated the Fright parameter. So the future direction will be that this work would help in design optimization of practical FSO links under adverse condition of fog and atmospheric turbulences. So that's it from my side. Thank you very much. If you have any question, you can ask me or you can write me here. So thank you very much.